It is the nature of mathematics that by the time we answer a question, we have 3 new questions. So as we learn more and more, we have more and more questions instead of less and less. What we're going to do today is just going to list subsets of a set. So let's start with a very simple set, say a 1-element set. So this set will have 2 subsets, the empty set and the set itself. Alright, let's move on to a bigger set, say set B, that contains the elements 1 and 2. So for subsets, there is going to be the empty set, there is going to be the set containing 1, the set containing 2, and the set itself, 1, 2. So that's 4 subsets. Now, as we move on to larger and larger sets, it will become more and more important that we're systematic. So the way we're going to be systematic is we're going to break down the listing by the number of elements in the subset. So let us work on a 3-element set C that has 1, 2, and 3 in it. Alright, so we have the 0-element subsets. That is just the one, the empty set. For 1-element subsets, well, we can have just 1 in the set, or just 2, or just 3. So there are 3 1-element subsets. For 2-element subsets, there is 1, 2, 1, 3, and 2, 3. And finally, for 3-element subsets, well, there is just the set itself. So we had 1 0-element subset, 3 1-element subsets, 3 2-element subsets, and 1 3-element subset. So altogether, 8 subsets. Let's see the subsets of a 4-element set D containing the numbers 1, 2, 3, and 4. For 0-element subsets, there is just the one, the empty set. For 1-element subsets, well, there is 4 ways we can pick one. So we're not exactly surprised that there are 4 such subsets. Now it's getting a little stickier. Let's see the 2-element subsets. So there is 1, 2, 1, 3, 1, 4. So we're done with the 2-element subsets with 1 in them. Let's roll up to 2, 2, 3, 2, 4, and 3, 4. Now notice that being organized or being systematic, one tool in it is the visual arrangement. See, I didn't write just one line. We have this nice triangular shape if we use the spatial arrangement as a tool of organizing. Now, for the 3-element subsets, I propose a new trick, and that is, instead of building up the subset from scratch, because 3 is almost 4, why don't we just start with the entire set and just pick one thing that we throw out from the set? So we could start with the set 1, 2, 3, 4 and kick out 1. Then we get 2, 3, 4. Or we can kick out 2, then we get the set 1, 3, 4. Or we can kick out 3, and then we get 1, 2, 4. And finally, when we kick out 4, we get 1, 2, 3. And for 4-element subsets, there is just one, the set itself. So let's see. For 0-element subsets, we had 1. For 1-element subsets, we had 4. 2-element subsets, we had 6. 3-element subsets, we had 4. And just one 4-element subset in a 4-element set. So altogether, we have 16 sets. There is a pattern here, right? If the set had 1 element, we had 2 subsets. If the set had 1 element, we had 2 subsets. If the set had 2 elements, we had 4 subsets. If the set, C1, 2, 3, had 3 elements, we had 8 subsets. And we had to work for it a little bit, but if the set had 4 elements, like 1, 2, 3, 4, then the number of subsets was 16. Do we predict that if we move up to a 5-element set, will we get 32? Even if you're already sure, it's not a bad idea to list all subsets. Let's list this one more and then I'll promise with stuff. You can fast forward. So let's say we're listing the subsets of the 5-element set E containing 1, 2, 3, 4, and 5. So for 0-element subsets, there is just one, the empty set, right? For 1-element subsets, well, we can predict 5 of them, right? It's either 1 alone, or 2, or 3, or 4, or 5 alone. For the 2-element subsets, let's see, that is 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5. We get this nice triangular arrangement. And the reason we're doing this listing is these are becoming interesting questions. How many 4-element subsets in a 10-element set? Right? By the time we figure out the total number of subsets, this broken down by the number of elements of the subset becomes interesting and more difficult. So let's see the 3-element subsets in a 5-element set. That's going to be tricky, even with the spatial help. That is 1, 2, 3. So to be organized, we're going to fix 1 and 2 and run with it as far as we can. 1, 2, 3, 1, 2, 4, and 1, 2, 5. Let's roll up to 1, 3, 1, 3, 4, 1, 3, 5, and 1, 4, 5. So these are just the ones that have 1 in them. Now let's roll up to 2. So that is 2, 3, 4, 2, 3, 5, 2, 4, 5, and finally 3, 4, 5. Okay, so now for the 4-element subsets, we're going to apply the same trick. So instead of building up the set from scratch, we're just going to grab the entire 5-element set and kick out just 1 element. So we can kick out 1, then we get 2, 3, 4, 5. We can kick out 2, then we get 1, 3, 4, 5. We can kick out 3, then we get 1, 2, 4, 5. We can kick out 4, then we get 1, 2, 3, 5. And finally, we can kick out 5, and then we get 1, 2, 3, 4. So notice right away that the number of 4-element subsets is going to be the same as the number of 1-element subsets, and with good reason. Because in a 5-element set, for a 1-element subset, we have to choose 1 out of the 5, but so do we for the 4-element subset. We just pick 1 element to kick out from the set, right? So there is some sort of symmetry going on here. Finally, for the 5-element subsets, there is just 1, the set itself. So now let's see how many subsets do we found. So the 0-element subsets, there was 1. For 1-element subsets, we had 5. For 2-element subsets, we had 4 plus 3 plus 2, that's 10. And probably the 3-element subsets was the trickiest. But now we could argue that we could have started with the set itself and just kick out 2. So selecting 2 elements to put in our set has to be the same number of ways possible as selecting 2 elements to kick out from our set. So we have 10 of each. We have 10 2-element subsets, and we have 10 3-element subsets of a 5-element set. The 4-element subsets, there were 5 many, and finally just 1 5-element subsets. So we have 20, 30, 32. So our suspicion was confirmed that if we move up to 5, the number of subsets is indeed 32. Will this keep? Will we get 64 next? But also we discovered, I promised you, that by the time we answer one question, we're going to have many others. There is some sort of a symmetry going on, even if we go back. Let's look at the 3-element subset. The 0-element subsets is the same as the 3-element subsets. Picking nothing to throw out. The 1-element subsets and the 2-element subsets, picking one number or picking one number to kick out. Now for a set with 3 elements, we just did the 4 elements, there is the symmetry again. 1, 1, 4, 4, 6. So the number of 1-element subsets in a 4-element set is the same as the number of 3-element subsets. Because here we pick 1 to select into our set, and here we pick 1 to kick out from our set. So there is this sort of outer symmetry that it looks like we have good reasons for that. Okay, the other new difficult question is, it looks like we're going to figure out how many subsets to a set. But what about this broken down? Like, for example, how many 3-element subsets in a 10-element set? So this is a new question that we bumped into as we were trying to answer, as it turns out, an easier. Now let's see how we could figure out what happens with 6 or 7 or 8. Will this doubling thing persist, or will we lose it? We just figured out that if we have a set E, so we just figured out that if we have a 5-element set, then there is 32 subsets. right? Now let us imagine that we write them into one long column. So there was the empty set, there were the one element subsets, there were the two element subsets, and so on all the way till the set itself. Okay, so here comes the trick. We're gonna copy this entire column. So we're gonna double it. And now we have the following. In each column, every single subset is different. And the same is true here. It's just that this is equal to this is equal to this, and so on. But we're gonna mess that up. So now here is what we're gonna do. Consider the set F, which we get by throwing in 6 into our old set. And now what we're gonna do, we're gonna go into the second column and we're gonna throw in 6 into every single set. So the empty set will become the set containing 6 only. The one element set 1 will become a two element subset, 1, 6. This will become 2, 6, 3, 6, and so on. The last one will become 1, 2, 3, 4, 5, 6. And now we have 64 subsets, right? Now remember that in each column, all the subsets were different, and here they remain different in the second column because we did the same thing to them. We just threw in the 6. And not one set from the first column equals to any set in the second column because the second column has subsets with 6 in them. The previous one doesn't. So we doubled up from 32 to 64 subsets. So this is what we call inductive reasoning, where we sort of build on our previous result to figure out the current one, and then we preserve that and we use that to figure out the next one. So we're building on our previous result. So a 6 element set has 64 subsets. We line them up to a long column. We repeat that column, and into the second column, into every set we throw in 7. That way we get 128 subsets. And notice that it doesn't even just double, but it has a very nice pattern here, because 2 is 2 to the first power, 4 is 2 to the second power, 8 is 2 to the third power. So it looks like the formula for the number of subsets is take 2, and as exponent, use the number of elements in the set. And that's how many subsets are there. Indeed, 32 is 2 to the 5th power. So a 5 element set has 2 to the 5th power, or 32 subsets. This is true. So this is our theorem, that if we have a set with n elements in it, then the number of subsets is going to be 2 to the nth power. Now, as it turns out that we can list all the subsets and then put them into a set. That's going to turn out to be an important set. And because of the size of this list, it's called a power set. I speculate because it's a 2 power. So the power set of a set is the set of all subsets to the set. I believe that if we start with systematic listing, we bump into this inductive way of figuring out the number of subsets. But now that we know the answer, there are easier, more intuitive, combinatorial ways to argue for that. Let us consider the set 1, 2, 3. Now, instead of listing all the sets, this is called constructive counting. Constructive counting is we're going to pretend to generate just one case, but we carefully follow how many choices we made while generating that one subset. So, imagine that we have to make a decision. We're generating a subset. Are we going to put 1 into that or not? That's 2 cases, 2 possibilities. Then we have the same question to decide about 2. Are we going to select 2 into our subset we're generating or not? And we have 2 choices with regards to 3. And therefore, we're going to have 2 times 2 times 2, or 8, such chain of decisions. We can actually, for example, a yes, no, yes would create the subset 1, 3, right? A no, no, no would create the empty set. A yes, yes, yes would create the entire set. We can also represent that using a tree diagram. We can say, the first question is, should we include 1? Well, we can have a yes or a no. And now, no matter what we did with number 1, we can ask the following question: what about 2? Do we want 2 into our subset we're generating or not? And again, there are 2 possibilities, yes or no. And finally, we can ask the same thing about 3. Problem with trees is they grow too big. So we have 2, 4, 6, 8 little ending. Now, a yes, yes, yes generated the set 1, 2, 3. A yes, yes, no generated 1 and 2. Yes, no, yes would be 1, 3. A yes, no, no would be just the 1. No, yes, yes would generate 2 and 3. We said no to 1 only. No, yes, no would have the one element set 2 in it. No, no, yes would be the one element set 3. And no, no, no would be the empty set. So that is our 1, 2, 3, 4, 5, 6, 7, 8 subsets. So this is now a combinatorial argument. So what are we left with? Now that we answered one question, we have the following questions. Is this outer symmetry universal? Will this stay with us? It looks like we have a very good argument. And second, if we have a 10 element set, we now know that it has 2 to the 10th power or 1024 many subsets. So now we have this more difficult, interesting question is what if we want to know how many 3 element subsets of a 10 element set? And so we answer the question, but we're left with 2 other interesting questions. Any questions? Are you sure? Thank you for watching.